Okay then. So we have gone through single phase AC circuits, and we have seen different theorems how to analyze a single phase AC circuit, and also seen uh, what are the different power terminologies and how to calculate average power, whatever it may be, apparent power. All these powers also we have seen. Okay, now we will move towards a three-phase circuit. This is a small chapter only. Okay, so this mainly deals with the three-phase this, AC system. Okay, so these are the topics we are going to cover in this three-phase AC circuits. So three-phase balanced system we will see. Okay, only balanced system we will discuss. Okay, in balanced system, star connected and delta connected, two types are there. Okay, so we'll discuss both. And next, wattmeter working principle. So basic working principle of wattmeter we will see. And after that, how to measure power in a single phase and three phase circuit using wattmeter. Okay, so these are the topics we are going to cover in this third chapter. Okay, right. So single phase system we have already seen, right? So what is the RMS value for single phase voltage? Hello?
Vm by root 2.
No. Okay, Vm by root 2. What is the RMS value of voltage, approximate RMS value of voltage which is coming to our house in India? Phase voltage. 230. Okay. So what could be the line voltage? You know what is the line voltage means and what could be that value? Any idea? Hello? You are able to hear me, right?
Yes, sir.
Okay. So can anyone guess what could be the line voltage in line? What is meaning of line voltage and what could be the line voltage in India? No idea. Okay. So line voltage is around 230 into root 3. So it is around 440 volts or 430 volts around it will come. Okay. All right. Anyway, we'll discuss all those things. Small. Okay, fine. Okay. So three phase system. Okay, actually speaking, we can have more number of phases also. Okay, initially study was carried out to have more than three phases also, but the complexity is going to increase. So that's why they have restricted the transmission or say AC system to three phase maximum. Okay. Uh, so what is with this three phase system? The most common polyphase voltage is a balanced three phase system. That means generally used system is three phase system. Okay. The source has three terminals. Okay. When you talk about source in the case of a single phase system, you have one phase and one neutral. Okay. But in a three phase system, you will have three terminals. Right. So they can be represented as A, B, and C, or R, Y, and B. Okay. So RYB stands for, this stands for what?
Red, yellow, blue.
Okay. So is basically the color code of the wires which you are going to use. Okay. So it is basically RYB in India. Okay. In different countries they adopt different colors. Okay. And neutral is basically black in color. Okay. And earth will be mostly in green color. Okay. Right. So three phase system has three line terminals, not counting the neutral or ground connection. You have three terminals for a three phase system. Okay. The voltmeter measurements will show that sinusoidal voltages of equal amplitude are present between any two terminals. Okay. So what it means? That means if you are connecting a voltmeter between any two lines. Okay, you will observe that it will have an equal amplitude. Okay, so that means between any two lines, if you connect, you will have a constant amplitude. Okay, between AB you connect, or BC you connect, or CA you connect, you are going to get a constant voltage value. Obviously, voltmeter will measure the RMS value of the line voltage. Okay, so that will be around 440 volts in India. Okay, right. So basically, it will have three terminals and one neutral connection. Okay, these voltages are not in phase. That means these voltages are not in phase. Okay, each of the three voltages is 120 degrees out of phase with each of the other two. That means there will be a 120 degrees phase shift between any two line voltages. Okay, if you are drawing the instantaneous waveform of all the three line voltages, you will observe that there will be a phase shift of 120 degrees, even line voltages or phase voltages, whatever you measure. Okay, and the sign of the phase angle depends on the sense of the voltages. Okay, right. So the phase angle, whether you want to consider plus 120 or minus 120, it depends upon the phase sequence which you are going to consider. Okay, that is called as basically phase sequence. Anyway, we'll see that. So basically what it states is it will have three balanced voltages. Okay, and the amplitude of the three phase voltages is going to be same. Okay, and they are not going to remain in phase. They will have a phase difference of 120 degrees. Okay, so that's what it means. So if you draw the with respect to time, if you plot the voltages, okay, you are going to get this kind of waveform. Okay, so you have VA voltage. Remember, this is phase voltage. What I have shown here is phase voltage. VA means the voltage of phase A with respect to neutral. Okay, so this is how the voltage of phase A is going to vary with respect to neutral. Okay, it's a sinusoidal fashion, and it can be given by this expression. Okay, Vm into sine of omega t. Obviously, Vb will be Vm sine of omega t minus 2 pi by 3. So 2 pi by 3 is nothing but 120 degrees. So there will be a phase difference of 120 degrees between A phase voltage and B phase voltage. When I say phase voltage, it is always the voltage of that particular line with respect to neutral. Okay, so that is called as phase voltage. Right. In single phase system also we have seen that phase voltage is voltage of one particular phase with respect to neutral. Okay, so here VA VB represents the voltage of that particular line with respect to neutral. Okay, so this is called as basically phase voltage, and VC is Vm into sine of omega t minus 2 pi by minus 4 pi by 3. That is nothing but minus 240 degrees. Right, so this is the general expression for phase voltages of a three phase system. Okay, voltage measured of any particular phase with respect to neutral. Okay, is it clear?
Yes.
Okay, right. A balanced load draws power equally from all the three phases of the source. What we have seen just now is called as a balanced source voltage. Okay, balanced means we have already seen 120 degrees phase shift should exist between any two phases, and the amplitude of each phase should be same. Okay, so if you see here VA maximum value is Vm, VB maximum value is Vm, VC maximum value is Vm. If you have same phase maximum value in all the three phases and there exists a 120 degrees phase shift, that means with respect to A, B is 120 degrees lagging, with respect to B, C is 120 degrees lagging. So if these two conditions are satisfied, then we call it as a balanced source. Okay. So in the present scenario, we are seeing a balanced source. Okay. If a balanced load is connected to that kind of balanced source, then the power drawn by all the three phases are equal. That means each phase will draw same amount of power from the source. That means the power drawn by phase A is equals to power drawn by phase B is equals to power drawn by phase C. Okay. This is called as a balanced load. Okay. When I talk about load, that means the same value of impedance is existing in each phase. Okay. Let's say you have R plus JXL. Okay. 5 plus J20, let's call. So if in A phase you have 5 plus J20, and in B phase also you have 5 plus J20, and in C phase also you have 5 plus J20, then that kind of load is called as a balanced load. Okay. So balanced load means same value of impedance in all the three phases. That is called as a balanced load. Okay. So balanced source is just now what we have seen. Okay. So if a balanced load is connected to a balanced source, then the power drawn by each phase is going to be same. Okay. So all three phases will draw the same amount of power. Okay. If you think more or you analyze more, at no instant does the instantaneous power drawn by the total load reaches zero. In fact, the total instantaneous power drawn is constant for balanced load. So what is the meaning of this statement? Can anyone say? Hello? Hello?
Yes, sir. It means the receives equal power at all instance.
So it means that the it at no instant does the instantaneous power by the total load reaches zero. That means at any instant of time, if you find the total power drawn by all the three phases, it is not going to become zero. Okay. Right. It is not at all zero at any instant of time. And in fact, the total instantaneous power drawn is constant. That means from a balanced source, if you are drawing a balanced load is drawing some amount of power, the three phase power drawn is going to remain constant. At entire time period, it remains constant. Okay. Even though the per phase power may be varying with respect to time, and it can become zero at some instant of time, but the total three phase power is going to remain a constant value. Okay. So when I say power, it is average power we are talking about. Okay. So for a balanced load, from drawn from a balanced source, the power drawn by three phases is constant. The total power drawn is constant. Okay. That's what this statement says. Okay. So this is regarding your balanced source and balanced load. If you talk about three phase system, basically they will call it as a double subscript notation. Okay. Since you have more number of phases, when I say voltage of phase A, I should say with respect to what? With respect to neutral or with respect to some other line. Okay. So always we should represent with double subscript notation. So you can't call voltage as VA. You should call voltage as VAB or VAN. Okay. If you say VAN, the voltage of phase A with respect to neutral. VAB, if I say the voltage of phase A with respect to phase B. Okay. So that's the standard usually we should follow. We should give a double subscript notation. Okay. So polyphase voltages and currents use double subscript notation. So for example, remember the instantaneous voltage is represented as VAB. If you are talking about instantaneous voltage, it is represented with small letter V and AB. That means the voltage of phase A with respect to phase B. Okay, instantaneous value. Okay, phasor voltages are represented as capital V AB bar. Okay, phasor you know already how to represent. Okay, so AB means the phase voltage difference. That means it's a phasor voltage between phase A and phase B. Okay, so which indicates the voltage of point A with respect to point B. Okay, so always subscripts indicates that the first letter in the subscript, that means that voltage we are measuring with respect to the second subscript in your notation. Okay, voltage of phase A with respect to B in the present scenario what I have shown here. Okay, right, so this is how you have to represent any voltage in a three-phase system. If it's a line, it will be VAB or VBC or VCA. If it's phase voltage, VAN or VBN or VCN. Okay, right, assume three-phase balanced system of voltages and representing below as. Okay, so we can represent a balanced three-phase voltages. Remember, these are phase voltages what I have given here. VAN phasor is equals to 100 at an angle of 0 degrees volts. Okay, right. So this is basically phase voltage. That means previously we have seen VA as Vm sine of omega t plus 0 degrees. So that means Vm is equals to 100. So VAN is equals to 100 at an angle of 0 degrees. Right. So simple phasor representation of your equivalent time domain function. Okay. So it is written as 100 at an angle of 0 degrees. Obviously, what should be VBN and VCN? If you are representing in terms of phasor, what should be VBN and VCN?
120, sir, lagging.
Okay, so 100 at an angle of minus 120. Okay, since we are talking about a balanced system, that means a balanced source voltage, right? So there will be a 120 degrees phase shift between different phases. So A is considered as 1 at an angle of, 100 at an angle of 0 degrees. Okay, so BN will be 100 at an angle of minus 120. If in case I am saying that I have a balanced source and VAN is equals to 100 at an angle of 40 degrees. Okay, what will be VBN? VAN is equals to 100
minus
at an,
160.
VAN is equals to 100 at an angle of 40 degrees.
100 at an angle minus 80.
Minus 60. Minus 160.
No,
Minus,
no, no.
minus 80, sir.
Okay, so it should be minus 80. So what it means is VAN is equals to 100 at an angle of 40 I am talking. So it is plus 40. For that plus 40, you have to add minus 180, minus 120 if you want to find out VBN. Right. So 40 minus 120, if you are adding, then you will get minus 80. Okay. So VBN will be 100 at an angle of minus 80 degrees. Okay. Right. Because always we should maintain a 120 degrees phase shift between the different phases. If you are considering one as your reference, others should follow that sequence. Right. I hope you understand, right? So there will be, if in case VAN is equals to 100 at an angle of plus 40 degrees, VBN will be 100 at an angle of minus 80 degrees. Okay. Right. That's called as a balanced system. Always 120 phase shift should be maintained. Okay. So if you have the set of voltages shown here, 100 at an angle of 0 degrees and VBN and VCN as shown here. So how to represent these voltages in a circuit format? Okay. So in a circuit format, if you see, we are going to show in this format. Okay. So if you more specifically speak, this is a star connected system. Anyway, we'll see what is star connected system in the later slides. Okay. So for understanding, we can represent the voltage VAN in this fashion. as shown here. That means what VN says is there is a voltage difference, RMS value voltage difference of 100 volts between A phase and neutral. That's what this 100 at an angle of 0 degrees means. So how I should represent? This is my phase A, and I should give positive terminal for phase A, and N means neutral, so I should give negative terminal for that, and it is a sinusoidal voltage, so I should represent with a sinusoidal waveform inside my diagram, and I should place 100 at an angle of 0 degrees volts. Okay, so what it means is the voltage of phase A with respect to neutral N is 100 volts at an angle of 0 degrees. Okay, so this is how you have to represent a source voltage. Okay, you are representing a voltage source, you are clearly specifying it is an AC voltage source, you are clearly specifying what is the difference in the voltage difference between terminal A and terminal N. Okay, that is 100 at an angle of 0 degrees volts. Okay, this is phasor voltage. That means voltage difference represented in terms of phasor value 100 at an angle of 0 degrees. Right. So how to represent VBN? Same thing, minus 120. Right. And VCN is plus 120. Okay. So can anyone say why I have taken VBN in this direction? Why not in the place of VCN?
Sir,
Sir,
since minus is
you
Sir,
put it
minus
on
120, sir. So it is
quadrant.
anti-clockwise direction, sir, rotation.
Okay.
So,
So
Clockwise.
okay, so this is a kind of representation which we are going to follow even when you go to phasor, then you will understand that in the same format I will show the phasor waveform also. What it means is, since we are saying VBN is minus 120 degrees, that means with respect to A, BN should be 120 degrees lagging. Okay, right, because vector phasors always rotate in anti-clockwise direction. So if I have plus 120, it should be rotated in anti-clockwise direction by 120 degrees. If it is minus 120, then I should represent it in the clockwise direction. I should move by 120 degrees. So that's why VBN is considered in this position. Okay, that is, it is behind your A phase voltage. Okay, and VCN, if you see, it is minus 240, or you can also call it as plus 120 degrees. Right, minus 240 and plus 120 both are same. So if you consider plus 120, it should be ahead of your A phase voltage. So that's why VCN is represented at this point. Okay, this is the way generally a star connected source voltage is represented. Okay, so I hope you are clear with respect to
Sir.
Yeah.
Sir, why it is 120, sir? Why not 90 or 60?
Why not 90 or 60? So if you talk about three-phase system, your single phase system time period is how many degrees? Single phase system I'm talking general time period, how much we will consider? Time period of a single phase system. You don't know? We have already seen, right? Okay. You know it or not? Single phase system time period. Time period, I am not talking about T. In terms of degrees, how much we will take? In terms of degrees, how much we will take?
2 pi by omega.
How much?
2 pi by omega.
2 pi, sir.
Okay. Okay. 2 pi radians, or in degrees how much?
360.
360.
360 degrees. Okay. Right. So your time period is generally 360 degrees we are considering. If you more specifically speak why it is only 360 degrees means it is actually coming from your generator. So generator is rotating with an in angular velocity over 360 degrees. Okay, so in clockwise or anti-clockwise, whatever it may be, so your generator is rotating with 360 degrees. Okay, so that is what in space, if you see your vector anything, if you consider, it can rotate 360 degrees angular motion. Okay, right, angular velocity. Right, so that circular rotation of your, which is happening in your generator, is coming out in the form of a time function, and that time function has a 360 degrees time period. Is it clear? So your question is why it is 3, why it is 120, but I am explaining why it is first 360. Okay, so the 360 degrees in a single phase system time period, which is 2 pi radians or 360 degrees, is actually coming from your generator. Generator will have a rotor which is rotating within that, and that rotor can rotate only 360 degrees. Okay, because in space with one axis it can rotate only 360 degrees angular motion. That angular motion is converted into a time function. Obviously you will have the same 360 degrees or 2 pi radians. That's why in a single phase system or in a 3-phase system, your time period t is considered for 2 pi radians or 360 degrees. Okay, that's how you have reached 360 degrees. Now within this 360 degrees, I want to create a balanced system. Okay, right, balanced system with more number of phases. Okay, if it's single phase, the complete time period, that means 360 degrees you can use. Now I want to create a balanced system with more number of phases. Okay, how many phases are here?
3.
So 3 phases. If I want to create a balanced system, the basic condition for balanced system is the phase difference between different phases should be equal. Okay, so if I create only 120 degrees phase shift only, that is possible. Okay, right. So that is the reason you have 120 degrees phase shift or 120 degrees what I have shown here is existing. If in case you develop a system which has 6 phases, let's say, in that scenario you will have 60 degrees phase shift between different phases. If in case you develop a 9 phase system, accordingly 360 divided by 9, how much degrees? So that much will be your phase shift between different phases. Okay, since we have standardized our system in India as well as in most of the foreign countries to 3-phase system, and 360 degrees your angular rotation maximum you can get. So that 360, if you are using 3-phase, you are going to get 120 degrees. If you increase the more number of phases, obviously that 120 degree will come down. Okay, right. Is it clear?
Yes, sir.
Okay. If you more specifically speak, in generator also you will have 3 phases, and physically each phase will be 120 degrees out of phase. That means physically when I say, if I place one conductor at let's say at what at one point, okay, the other B phase conductor will be 2 pi by 3, that means 120 degrees. It will come back and at that point it will stay. You are understanding? In space, in a generator, if you talk, you will talk in terms of space. That means in terms of angular motion you will talk. Okay, in a generator in 3 phases you will have, let's say, 3 conductors are there in each, one conductor in each phase. The first conductor, if you are placing at 0 degrees, the second conductor you will place at 120 degrees. That means phase B. Okay, so that 120 degrees which you are physically creating difference in space, that will be reflected as 120 degrees in time domain also. I hope you got it. Okay, right. But anyway, so for your question, the answer is, since the 3-phase system we are dealing and 360 degrees divided by 3, so that's why you are going to get 120 degrees phase difference between different phases in a 3-phase system. If you increase the number of phases, accordingly you have to create the phase difference. Okay, right. So I hope you are clear with the notation, how to represent a voltage source, how to denote your subscripts VAN, VBN, and VCN, and how to show the 120 degrees phase shift. So this is how you have to consider, right? Okay, so just now we have seen what is voltage VAN, VBN, and VCN given by these three expressions. Okay, if I want to find out what is the phase voltage VAB, okay, the voltage VAB can be found, right? The voltage VAB can be found by seeing the subscripts. That means VAB is equals to VAN plus VNB or VAN minus VBN, right? So what it means, VAB is the voltage of phase A with respect to phase B. That's what we are talking about. The first subscript is phase A, so that means voltage of phase A we are talking with respect to phase B. Okay, so VAB can be represented as VAN plus VNB or VAN minus VBN. Okay, that means voltage of phase A with respect to neutral you are finding, and voltage of phase B you are finding with respect to neutral, and difference of those two, AN minus VBN, will give you VAB voltage. Okay, so here right hand side I have given the phase voltages, that means voltage of phase A with respect to neutral, and I am trying to find out the line voltage. Anyway, now line voltage terminology will come later. I am trying to find out the voltage VAB. So try to use these, substitute these phasors in this expression and try to find out what could be the value of VAB. Simply substitute VAN and VBN in this expression and find out VAB phasor value.
Sir, 173.2 at an angle of 30 degree.
Oh, you have solved or you already remember that?
Sir, I have solved.
Okay. So fast. And then did anyone else got that answer?
Sir, 100 at an angle of minus 60.
100 at an angle of minus 60. Okay. So anyone else? Please try to solve it and let's check whoever is getting what answer and which is correct finally we'll see. Simply substitute those phasors and you can use your calculator or whatever it may be, it's up to you.
Twenty-three point two at the angle of 29.9 degree.
Okay.
Sir,
29.9
sorry, sir, 173 at an angle of 30.
at an angle of 30. Okay. So some of you has got some answer and some people have told different answer. So let's see that. So how to do that? 100 at an angle of 0 degrees minus 100 at an angle of minus 120. Okay. If you have a calculator, you can directly substitute and find the reference, or otherwise you have to use cos theta minus j sin theta formula, right? So if you do that, 100 at an angle of 0 degrees, right? So it will be 100, and talking about this thing, so 100 into cos of minus 120 plus j into sin of 120. So if you do that, right? So cos of minus 120, maybe you will get 1 by 2. Okay, so you will get 50 plus j 86.6, and if you solve this you are going to get 173.2 at an angle of 30 degrees. Okay, so 29.9 or 30, whatever it may be, it is equivalent to 30 degrees only, right? So you are going to get 173.2 at an angle of 30 degrees. Okay, so that means for a balanced system, if you are considering two phases, that means you are finding the voltage between any two phases, you are going to get a magnitude of 173.2 volts and a phase angle of 30 degrees. Okay, remember that this 30 degrees is coming with respect to your VAN. You are understanding now? The phasor reference what we have considered is VAN is equals to 100 at an angle of 0 degrees. So that means with respect to VAN, VAB is going to have a 30 degrees leading angle and magnitude of 173.2 volts. Is it clear? So with respect to AN, you are going to have AB 30 degrees ahead. Okay. So what could be the phasor diagram? If you draw the phasor diagram, the three given voltages and the construction of the phasor voltage VAB are shown in the phasor diagram. So this is the equivalent phasor diagram of these expressions. Right. So VAN is 100 at an angle of 0 degrees. VBN lagging this VAN by minus 120. VCN leading this VAN by plus 120 or lagging VAN by minus 240. Okay. And VAB will be as per this expression. It should have a larger amplitude root 3 into 100 and it should have a phase angle of 30 degrees leading. Right. So this is how you have to draw a phasor diagram for the given phase voltages and the calculated voltage VAB. Okay. So with respect to your reference VAN, which is at 0 degrees, your AB is going to lead by 30 degrees and amplitude is root 3 times more than the amplitude of your phase voltage. Is it clear? The double subscript notation can be applied to currents also. That means similar to voltages what we have seen, similarly for currents also you can use the same subscript notation. That means IAB, if I say, is the current flowing from A to B. That means phase A to phase B, what is the current that is flowing? Okay, so that is represented as I bar AB in terms of phasor. Okay. So this is the basic concept regarding your plotting of phasor diagram and terminologies for phasor voltage and how to calculate VAB. Okay, right. So is it clear to everyone or anyone has any doubt in this? If anyone has doubt, ask me. Okay, so no doubts, right?
Yes, sir.
Okay,
Sir,
fine.
double subscript notation means?
So subscript means this. If I represent a phasor V, AB is called as subscript. That means this is the voltage actually. So this V indicates I am measuring some voltage. Okay, and bar indicates it's a phasor. Okay, and AB is the subscript. Okay, so instead of having only A, we are having A and B. Okay, so you have two subscripts. One is A, another one is B. Okay, that's why we will call it as double subscript notation. Okay, what it means is voltage, phasor voltage of A with respect to B. That's what it means. Okay, since we are talking about a three-phase system, always you will have more number of terminals. In a single-phase system, if I say line voltage is so and so or phase voltage is so and so, it is always indicated that it is with respect to neutral. Okay, because you have only phase and neutral, that's all. But in a three-phase system, you have three phases and one neutral. So when I specify some voltage, I should be very specifically say that voltage is with respect to which terminal. Okay, If it is with respect to neutral, I will call it as VAN. If it is respect to some other phase, I should represent that phase label here. That means B or C or N or whatever it may be. Is it clear?
Yes, sir.
Okay. Right. So we have seen, yeah, any doubt? Yeah. I am not able to hear your voice. Sorry, I am not able to hear your voice at all. It is breaking. Hello. Yeah.
Hello, sir. Sir, can it be V at the subscript of A, B, C?
No. We can't say like that. What?
Between vector VC and VAB, we can't have.
You mean 3 subscripts V, A, B, C?
Yes, sir.
No. You can't say, because when you talk
Sir,
about
previous slide. Sir, previous slide, sir, please.
yeah,
Sorry, that vector between VC and VAB can't have according to parallelogram.
VC and
VAB.
you want to calculate between this
Parallelogram.
and this one.
Yes,
Do you
sir.
want to
That
calculate between
parallelogram.
this one? Okay. That means you are trying to find out some other voltage.
Yes, sir.
So you can't say like VCAB. Okay. You can calculate the voltage between those two phasors. Okay. You have VCN and you have VAB. If you want, you can find out what is the phasor addition or subtraction of that. Okay. But your VCAB, if you say, that is not, a standard form of representation. Maybe we can understand from seeing the phasor diagram. Okay, it is the phasor addition of VCN plus VAB. Okay, so in that scenario, maybe you have to specifically say that you can't write VCAB. You can write VC with a small hyphen AB. You are understanding?
Yes, sir.
You can say VC with a small hyphen AB. Okay, so but even this is actually not a standard form of representation, but mathematically you can write, not an issue. What it means is you are adding a phase voltage to a line voltage. Okay, that's what it means. Line voltage is VAB and phase voltage is VCN. So you are adding a phase voltage and a line voltage. Of course, even though these are phasors, they can be added. Even if you see an instantaneous value of that, also you can add, right? Because adding of phasors, you should have positive amplitude and you should have same frequency. Okay, so since AB phase frequency is 50 Hz and CN frequency is 50 Hz, there is nothing wrong, you can add it, no issue. But you have to specify like VC small hyphen with AB. Okay, so that will give a clear picture. Okay, if you simply write VCAB, then people can think like it is VCA with respect to B. You are understanding now? Right. So if I write VCAB, I can call it as VCA with respect to B. That is also possible. I can assume like that also. Okay. Right. So if you put a small hyphen, then it indicates the voltage of phase C with respect to AB voltage. Okay. So this is for our understanding, this notation was given. Okay. So If you want, you can do like that, but that kind of situation mostly it will not come in even in real system also. Okay. But there is nothing wrong if you want to represent like that, but you should put a hyphen in between those two. So you are just indicating differentiating. That means I am measuring the voltage of AC with respect to AB. Okay. Okay. Right. So 3-phase 4-wire star connected system. Okay. So when you talk about a star connected system, you will have 4 terminals. Okay. 3 are already we have seen, which is ABC or RYB, and one more terminal will be there, which is called as a neutral. Okay. The 3-phase source has 3 terminals. Okay. And these 3 terminals may or may not have a 4th terminal, the neutral connection. Okay. Sometimes in a 3-phase system, you will not have the neutral wire. Okay. So that is basically called as a delta connected system. Okay. But in a star connected system, that means if a neutral is present, it may be represented by 3 ideal voltage sources connected in star fashion, that is terminals A, B, and C, and the neutral N, as shown below. So, okay, so if you have a neutral wire, then it is called as a star connected system. Okay, so what it means is, if you have only 3 terminals, it can be called as a delta connected system. If you have, that means delta connected system will not have neutral. Star connected system can have neutral. If you want, if you don't want neutral, you can remove that neutral also. Okay. So star connected system, both are possible. Okay. 3-phase 3-wire is possible. 3-phase 4-wire is also possible. But generally 3-phase 4-wire is the preferred one. Okay. Right. So 4th wire will usually exist in a star connected system. So this is how you have to represent a star connected 3-phase 4-wire source. Okay, so this is your neutral N, this is your A phase voltage, B phase voltage, and C phase voltage. Okay, VAN, VBN, and VCN. Okay, here now if you see, your B voltage is lagging your A voltage with respect to 120 degrees, and C is lagging with respect to A by 240 degrees. Okay, A, B, and C. Right. Okay, so this is how you have to represent a 3-phase 4-wire star connected system. So we have already seen what is balanced condition means. Their amplitude should be same. Okay, so amplitude of VN is equals to amplitude of VBN is equals to amplitude of VCN, and this is one more condition. That means phasor addition of VAN plus VBN plus VCN is equals to 0. Okay. If these two conditions are satisfied, then we can call it as a balanced star connected source. Okay. This third condition is nothing but your 120 degrees phase shift. Okay. That 120 degrees phase shift, what we have already discussed, can also be called in this fashion also. Phasor addition of AN, BN, and CN is equals to 0. Okay. So if these two conditions are satisfied, then we can call that source as a balanced source. Okay. These three voltages exist between one line and neutral and are called as phase voltages. Okay, right. This VAN, VBN, and VCN are basically phase voltages. If we choose VAN as the reference and define VAN is equals to VP at an angle of 30 degrees. Okay. VP is used to represent the RMS value of phase voltage. What it means is VAN will have some magnitude, right, and some amplitude will be there. If I represent that amplitude as VP, okay, so VP at an angle of 30 degrees, sorry, I think so, once again. So this should not be 30, this should be 0 degrees. Okay, right, so it is my printing mistake. This should be 0 degrees. Okay, Right. So if I represent VAN as my reference phasor and VAN is equals to VP at an angle of 0 degrees, I can represent. Then VP is the RMS value of phase voltage. If you remember, phasors can have two types of representation. One RMS value with some phase angle or maximum value with some phase angle. Both are correct. Okay. Generally, RMS value with some phase angle is what usually followed. Okay. Right. So VP here represents the RMS value of phase voltage at an angle of 0 degrees. Okay. So what could be VBN and VCN? If VAN is equals to VP at an angle of 0 degrees, what will be VBN and VCN?
Sir, VBN
Sir,
equal to
VBN.
So
VP at angle of
VP at the angle of
120.
120.
VBN is equals to VP at an angle of
Minus 120.
minus 120 and VCN will be
VCN
VP at an angle
VP
of
at the
minus
angle of
Minus
minus
240
240.
degree.
okay minus 240 or plus 120. Okay, right. So this is because the amplitudes are same, that means the RMS value of your phase voltage is same, so I can use as some constant, I mean some representation as VP. Okay, right, because we are talking about a balanced system. If it's unbalanced system, we can't represent like that. Okay, right. So in a three-phase balanced system, if I consider one as my reference phasor, okay, let's say VAN is equals to VP at an angle of 0 degrees, then VBN and VCN can be represented by these three set of equations. And if you draw the phasor diagram for this, it can be shown in this fashion. Okay, this is already we have seen. Okay, right. But this is called as positive sequence. Okay, so positive sequence means ABC sequence. Generally, if you see here, this is called as ABC sequence. What the sequence means says is positive sequence means ABC sequence that you remember. What it indicates is with respect to A, B phase will be minus 120. With respect to B, C phase will be again minus 120. Okay, so that's what ABC sequence or positive sequence means. Okay, that means A is considered as your reference, B is going to lag this A by 120 degrees. And C is going to lag your A by 240 degrees. Okay, that's what ABC sequence means. There is an opposite sequence for that is called as negative sequence or ACB sequence. Okay, this is called as a negative sequence. Okay, in that scenario, if you talk about negative sequence and if you take VAN is equals to VP at an angle of 0 degrees, then your VBN will be VP at an angle of plus 120 and VCN is equals to VP at an angle of plus 240. You are understanding?
Sir, what is VP, sir?
What is?
We are
Okay.
using VP, no, sir.
Yeah, VP is the RMS value of your phase voltage. Okay. So for your home, your RMS value is 230 volts. Okay. Right. So if you have a three-phase system and if it is balanced, only when it is balanced only I can use this representation. Okay, if it is balanced, it is 230 at an angle of 0 degrees, 230 at an angle of minus 120, 230 at an angle of minus 240. Okay, so since the 230 is same in all the three phases, I am representing with a common letter or common representation which is called as VP. That means P represents phase voltage and V is your actual value. That means phase RMS voltage. Is it clear?
Yes, sir.
Okay. P represents phase and V is the voltage and it is RMS value I am saying. So it will be 230 at an angle of 0 degrees. So since I am writing 230 again and again, I am simply representing with VP. Okay, so VP represents the RMS value of phase voltage. Okay, so is it clear with positive sequence and negative sequence?
Sir, these two are equivalent or not?
No. These two are not equal because we can't say it is equal. Even though the amplitudes are same and phase difference is same between different phases, the phase difference angle is going to have a different impact, because if you see the algebraic sign here, VBN is minus 120.
Minus.
Here it is plus 120.
Plus.
VCN is minus 240. Here it is plus 240. Okay, right. So what it indirectly means is, in positive sequence case, BN is lagging with respect to A, but in negative sequence case, BN is ahead of 120 degrees, ahead by 120 degrees with respect to A. Okay, so that means after A you will have C, after that you will have B. Okay, is it clear? The sequence is reverse. Okay.
Yes, sir.
How can you
Yes,
achieve
sir.
this? How can you achieve this? Let's say I have a generator. Okay, I'm simply saying what. Do you have any basic idea regarding generator? What could be the different, parameters or elements that can be there? Okay, what is the input for a generator? Input means mechanical input or electrical input.
Mechanical.
input.
Okay, so how you are going to give mechanical input to that?
Fuel or sir?
By using electromagnets, sir.
No, input I am talking about.
Sir, fuel.
Okay, some fuel, or if you consider a hydro generating station, some blades will be there, on that water will fall and blades will rotate. Correct na?
Yes.
So that means you are trying to rotate your rotor. Okay, rotor is one which is rotating because water will fall on the blades and blades will keep on rotating, and that blade system will be connected to your rotor. So something like a rotor will be there which is rotating part in your generator. Okay, and on the stator you will have 3 phase windings. Okay, so A phase winding will have, B phase you will have, C phase winding, 3 windings will be there. Okay, so if that water is falling okay, from top, and your blades are rotating in clockwise direction, then you will get, let's say, positive sequence. If I make the water to fall in the opposite direction and make the rotor to rotate in the anti-clockwise direction, then you will have this kind of sequence. You are understanding? That means in the generator, if your rotor is rotating clockwise, you will have, let's say, positive sequence. If your rotor is rotating anti-clockwise, you will have negative sequence. Okay, right. So this is, basic idea I want to give you. That's all. So what is the practically how it is going to come? Okay, so these 2 phase sequences are coming from your generator, and if your rotor is rotating clockwise, you can get positive sequence. And if you are not doing any changes in your generator, and if you are trying to rotate your rotor in the anti-clockwise direction, and you are not touching your generator at all, no connections are changed, then you will get this negative sequence. Okay, right. So one is called as positive sequence, another one is negative sequence, and generally positive sequence is one which is usually followed in any system. Okay, right. Is it clear? Only phase angle is your difference. That's all.
Sir.
Yeah.
So then output will be different.
Output will not be different. Only your phase sequence will be different.
Okay, sir.
See, your phase voltage, if you talk, your voltage amplitude is constant. Okay, it's not going to change. Okay.
Yes, sir.
Your phase angle for your reference is also going to remain same, 0 degrees only, because that is your reference. Only thing is, since you have made the rotation in the opposite direction, your B phase will have the phase angle will be different. In this case, if you have plus minus 120, you will have plus 120 here. Okay, that's all. Only the phase angle will be varying. That's all. Remaining all things will remain same.
Okay, sir.
Okay.
Once before slide, sir.
Yeah.
Okay, sir. Thank you, sir.
Okay. So that is regarding phase sequence. Next, we'll see what is line to line voltage in a star connected source. Okay. So this is already we have seen. Okay, but I have not specified that is a star connected system. So now I am specifying it is a star connected system. Okay. So the line to line voltages are often called as line voltages. Okay. That means if you are measuring a voltage of one particular line with respect to some other line, then it is called as a line voltage. From the phasor diagram, it is clear that line voltages are 30 degrees leading with respect to the phase voltages, and the phase difference between VAB, VBC and VCA is 120 degrees. And VAB leads VBC by 120 and VBC leads VCA by 120. Okay. So if you consider a three-phase star connected system, this is how you have to represent your phase voltages. We have already seen VAN, VP at an angle of 0 degrees, VBN and VCN. If I want to calculate VAB, how to do that? VAB is equals to VAN minus VBN. So this is your VBN. You take it in the opposite direction. So then you can place a minus here. So minus VBN. So this minus VBN added to this VAN will give you your line voltage VAB. Okay. So if you want, you can apply the parallelogram law also. If this is VP, so root of VP square plus 2 into VP into cos of angle between these two. What is the angle between these two? Angle between minus VBN and VAN.
60.
60. Okay. So if you want, you can apply parallelogram law, or you can substitute your phasor voltages and calculate. So we have already seen that, and you are going to get a line voltage of root 3 into VP at an angle of 30 degrees. Okay. In the previous case, we have considered VP is equals to 100. So if you consider VP is equals to 100, you will get the same value what you have already seen. Root 3 into 100, which is 173 point something at an angle of 30 degrees. Okay. So these are called as phase voltages, VAN, VBN and VCN, and VAB is called as a line voltage. Okay. So what you could observe from this line voltage? Two observations can be made with respect to the line voltage. Okay. With respect to your phase voltage. If the RMS value of line voltage is denoted by VL, the important characteristic of star connected three-phase system is VL is root 3 times that of VP. That means the RMS value of line voltage is always root 3 times more than the RMS value of phase voltage. Okay. Clear. So for a balanced system, this is always going to remain same for a star connected system. Okay. And what is the phase angle of this line voltage? It is 30 degrees leading with respect to the corresponding phase. Okay. If you have taken VAN is equals to VP at an angle of 0 degrees. So VAB is 30 degrees ahead plus 30. Okay. So that's what it is written here. VAB is equals to root 3 into VP at an angle of 30 degrees. If you consider root 3 into VP as VL, so that means VL at an angle of 30 degrees. What will be VBC and VCA? What will be VBC? Line voltage? You are able to hear me, right?
Yes, sir.
Okay, so VBC will be, this is already 30 degrees. So since it is a balanced system, VBC should be minus 120 with respect to VAB. Okay, so for this 30 degrees, you have to add minus 120. So that will result in minus 90 degrees. So you can call it as VL at an angle of minus 90. And VCA is VL at an angle of minus 210. Okay, with respect to AB, it is minus 240. So 30 minus 240, that will give you minus 210 degrees. If you have any doubt, you draw the phasor diagram for AB. I have already drawn. For BC, where it will fall? It will fall somewhere between these two. Okay, AB, BC, CA, na? So B is here, C is here. So somewhere here you will get. Okay, if you want, you can apply parallelogram and find out. You will observe that you will have minus 90 degrees. Okay, is it clear? Since it's a balanced system, I can write straight away minus 120 and minus 240. If you have doubt, you can draw the phasor diagram and find out. You will observe that these angles will come for AB, BC and CA. Okay, and we have already seen for phase voltages, the phasor addition of all the three phasor voltages is equals to 0. Similarly, the phasor addition of all the line voltages is also equals to 0. VAB phasor plus VBC phasor plus VCA phasor is equals to 0. Okay, right. So this is for star connected system line to line voltage. Okay, anyone has doubt in this?
No, sir.
Okay, so no doubts. Right, so we have seen how to represent phase voltages and how to represent the phase angle difference between them. We have already seen what is line voltage, and line voltage will be √3 times more than the RMS value of your phase voltage, and it will be 30 degrees leading with respect to that corresponding phase. Okay, so can anyone say where will be AB? I have wrong now. BC, where will be BC? Where BC will fall?
Between VBN and VCN.
You mean here?
Sir, between VAN and VBN.
VAN and VBN. Okay, so just now I have told it will fall in between these two, but if you think properly, it will not fall in between these two. Okay, I am saying that it is minus 90 degrees. So with respect to AN, it should fall minus 90 degrees. That means it will exactly fall here, vertically downwards. Right. Why means VBC indicates VBN minus VCN. So minus VCN will fall in this direction. How minus VBN has fallen opposite to that. So similar to that, VCN is here. Okay, minus VCN will be falling here, right? And the phasor addition of those two should fall somewhere in between those here. So it will be exactly 90 degrees downwards in this direction, right? Is it clear? So you'll
Yes,
have
sir.
minus 90 degrees and minus 210 degrees for VCA. Okay, right. So these are the voltages, line voltages. You can simply add minus 120 to the reference phasor, or you can draw the phasor diagram and check where it is falling also. Okay, right. So this is how you have to represent your line and phase voltages for a star connected system. Okay, so now it's 11:25, so 11:35 we will meet. Okay, so 10 minutes break you can take. So after that we will continue our discussion. Okay.